Hello there and welcome to the October 2020 paper. Here we're looking at question 8, the proof by induction question for the paper. So proof by induction that for z equals the positive integers f of n, which is 2 to the power of n plus 2 plus 3 to the power of 2n plus 1, is divisible by 7. So let's get started in part 1. Prove true for n equals 1. So f of 1 is going to equal 2 to the power of 3 plus 3 to the power of 3 as well. So let's just do that in the calculator quickly. 2 to the power of 3 plus 3 to the power of 3. Oh, whoops, I did that incorrectly. 2 to the power of 3, side button, plus 3 to the power of 3 is 35, which is divisible by 7. Good. Let's move on to part 2 now. Part 2 is to assume theorem true for n equals k. So therefore f of k equals 2 to the power of k plus 2 plus 3 to the power of 2k plus 1 is divisible by 7. Moving on to part 3 now. We need to now prove our theorem true for k plus 1. Prove theorem true for n equals k plus 1. So what we effectively want to show is that 2 to the power of k plus 3 plus, if we put k plus 1 in there, that will give us 2k plus 2 plus another 1, 2k plus 3, oops, 3 to the power of 2k plus 3 is divisible by 7. Okay, this is what we want to show, so let's now get started on it. 2 to the power of 2k plus 3 plus 3 to the power of 2k plus 3. Now, the first thing I do on these questions is reduce the powers on the indices here down to what they were in your assumption step, because we're going to have to bring in that assumption at some point, so we need to reduce the powers down to what they were in the assumption stage. So what I'm going to do is split up the indices. I'm going to do 2 times 2 to the k plus 2 plus, I need to split up this into 3 to the power of 2k plus 1, so we need to take off 2 powers of 3 here, so that's going to be 9 times 3 to the power of 2k plus 1. Because I've taken off 2 powers of 3 there, 3 to the power of 2 is 9. So now that our powers are down to the same powers that we had in the assumption step, I'm now going to do a very cheeky factorising step. I'm going to factorise 2 to the front, and then I'm going to put in my assumption into the brackets. 2 to the power of k plus 2 plus 3 to the power of 2k plus 1. Now if we look at what we've got here, this thing inside the bracket here is our assumption. So this thing here is divisible by 7. But it's not equal to the line above, because if I expand the brackets, I'll get the first term fine, but I'll only get 2 lots of this 3 to the power of 2k plus 1. But I don't want just 2 lots of this expression at the back, I want 9 lots of this expression at the back. So therefore I need 7 more of this power of 3 to the power of 2k plus 1. And, nicely, this thing here is also divisible by 7. Divisible by 7. So there we are, we have 2 things that are being added together there, both being divisible by 7. We just need to write a little conclusion to that effect, just to finish off part 3. As the sum of 2 multiples of 7, my pen's a bit lagging here now, as the sum of 2 multiples of 7 is also multiple of 7, is also a multiple of 7. F of k plus 1 is a multiple of 7. Okay, so there we are. That's the finished bit for part 3, but that's not our final conclusion. Let's now state our final conclusion. If you want to skip to the end of this video, you're very welcome to do that. It's going to take a little while because my pen's a bit laggy today. But the conclusion is, as we have proven our theorem true for n equals 1, and assuming our theorem true for n equals k, we have proven our theorem true for n equals k plus 1. Therefore, by induction, our theorem is true. By induction, 2 to the power of n plus 2 plus 3, 3 to the power of 2n plus 1 is divisible by 7. For n existing in the z plus. It's really important you put that little back bit there, that z n exists in the z plus, because that's the only thing that our theorem works for. It's the only set of values for n our theorem works for. It doesn't work for if we try to put in some negative values for n. It doesn't work if we try to put in some fractional values for n. It only works for whole positive numbers. That's the essence of proof by induction. You can only use proof by induction to prove for whole positive numbers. And there we are. That's the answer to our theorem. Put the little box at the end there. So there we are. That's 6 marks there for question 8. Let's now move on to question 9.